We are talking about similar triangles today. Have you guys heard or have learned the term similar in math before? Do you have? See some heads nodding, some heads shaking no. So that's fine. Some of us may know, some of us may not. The idea of similarity in triangles is very, very simple. Let's take a look. We got triangle ABC here, this tiny one. And we got triangle XYZ, this much larger triangle. All right? Now the first question we want to ask is, are these two triangles congruent? Give me a thumbs up if you think yes, they are congruent. Give me a thumbs down if you think no, they are not congruent. What would you say? We've talked about congruent before. I see some thumbs up. I see some thumbs down. I see more thumbs up than down. That's interesting. Does anyone remember what congruent means? Same what? There's two things that they have that are the same. Same size and same shape, which is same angles, right? Do these look like they're the same size? No. One's tiny, one's big, right? So if they're different sizes, obviously they are not congruent. So if you had your thumb down, you were absolutely right. These are not congruent because they are different sizes. Now, are they shaped the same? Yeah, they're slanting on the left side at the same angle. This right side looks like it's about the same. Right? When it comes to the overall shape of the triangle, they are the same. So they're different sizes. We could say, but shaped the same. This is basically what similar figures are. It's like partial congruency. They're shaped the same, but they're different sizes. So we see in triangle ABC, we've got a 41-degree angle at angle A, a 58-degree angle at B, but we don't know what C is. For triangle XYZ, I know that Y is 58 degrees, Z is 81 degrees, but I don't know what X is. Is there a way we can figure out what those third missing angles are in each triangle? Add them up, A plus B plus C, that's right, and set it equal to 180. What do we call that? Do you guys remember? Triangle sum theorem. Absolutely. Now you may just know the equation, A plus B plus C equals 180. That's fine too. Test isn't going to ask you what's the name of this theorem. As long as you know how to use it, that's what matters. So we could set up an equation for my first triangle here. A plus B plus C equals 180 degrees. Like I said, I know that A is 41 degrees. I know that B is 58 degrees. But I do not know what angle C is. So I'll leave it as C. All right, let's go ahead and solve this, and then we'll go to XYZ. If I want to get C all by itself, what do I need to do first? Even before we subtract, there's something we can do. Combine like terms. Exactly. What is 41 plus 58? 99. Plus C equals 180. Now what can I do? Subtract. That's right. Someone said it. We subtract the 99s. And we're left with C equals what? 81 degrees. So there's my missing angle, 81 degrees. Any questions on how we got there? Okay. Those last Monday's lessons should be pretty straightforward. We did really good with that. Breezed through it. Now let's go to XYZ. So I don't know what angle X is. Right, that's a question mark, so I'll just leave it as X. I know that angle Y is 58 degrees. And I know that angle Z is 81 degrees. So now I set it up the same way, and I can now solve for x. I'll combine like terms on the left, and then we know what 58 plus 81 gives us. 139. Beautiful. And what can I do now again to get x by itself? Subtract 139. Exactly. So what's left for my angle x? 180 minus 39 gives me 41 degrees. That's right. I'll put you on it. Kevin, go ahead. Pass this over here. Yeah. Here. So take a moment, compare these two triangles. We know that they're different sizes, but by doing this, what did we just find out about the missing angles? They're not equal to each other, right? One's 81 and one's 41. But if we go back, right, we found that angle C was 81 degrees. We found that angle X was 41 degrees. What do we notice about these two triangles? All three angles are the same. Thank you, Moses. My top angle's 41. My bottom left angle's 58. And my bottom right angle's 81. So what we just did was we proved these are shaped the same despite being different sizes. Right? If all three angles are exactly the same, these triangles are similar. So if we want to answer the question, what do we find out about the missing angles? We would just say all three angles in both triangles are exactly the same. All three angles in both triangles are exactly the same angle measures. Therefore, these triangles, and this is what we'll get into on the next sheet, are similar. Okay, put it away, please. So this idea of similarity, right? If I were to say, oh, you and your friend, you look very similar, right? That means that there's some aspects of your appearance that are the same, but some that aren't. Now, if you had an identical twin, and I said, oh my God, you guys look exactly alike, that means that you look exactly alike. Pretty straightforward, right? So you can think of like identical twins as being congruent, same size, same shape, everything about them is the same. But maybe you and your older sibling, you could say you guys look similar, right? You probably don't look exactly like your older sibling. Maybe you guys have the same eyes, the same nose, the same hair, but there's certain aspects that are different, right? So similar is just a toned down version of congruent. So figures that are similar, like we said, have the same shape, but different sizes. Imagine the exact same t-shirt. One's in a size small, one's in a size XL. Right? Just because it's an extra large doesn't mean the sleeves are now long sleeves. Right? If it's the same shirt, they're similar figures. They're shaped the same, but they're different sizes. So these two shirts would be similar. Now, if I took a hoodie and a crew neck, right, one has a hood, one doesn't, those wouldn't be similar because they're not shaped the same, right? So we know that triangles are similar if their corresponding angles are congruent. So if they have all three of the same angles like we just found with the two triangles previously, all of those angles were congruent, right? 58, 81, 41, I think. But their side lengths have to be proportional. Proportional. This is super important. Their angle measures are the same, but their side lengths are proportional. Setting up proportions is exactly what we're going to be doing today. So if we look at triangles ABC and DEF, we're given the information that they have all the same angle measures. So we're not solving for angles anymore, like we've been doing. What we're going to be doing is solving for a side length. So we can use what we know about proportions to solve for x here by setting up an equation. This is where things can get a little bit confusing, so make sure you are following along. I want to make sure this comes across in the best way possible. Let's see, let's do this. So, if I've got triangle ABC, I know that one side, this side BC, is 6 units long. And I know my bottom side, AC, is 7 units long. Okay, the right side is 6, the bottom is 7. If I put the right side over the bottom side, I now have the fraction, or proportion, 6 over 7. The ratio from my right side to my bottom side is 6 to 7. If I go over to triangle DEF, I want to set up the same proportion using corresponding sides. So that means if my numerator is the right side of my triangle in the first fraction, then my numerator has to be the right side of my triangle in the second fraction. EF, which is x. If my denominator in the first fraction was the bottom side of my smaller triangle, then the denominator of my second fraction is also going to be the bottom side of my larger triangle, which is 14. What questions can I answer about how we set that up? Now, there's a couple different ways to set it up. I would say that this way is probably the easiest way to understand. Right side over bottom for triangle 1, right side over bottom for triangle 2. Right, if we say this is triangle 1, this is triangle 2. We set those side lengths up in a proportion, which just means fraction, and we set them equal to each other. Triangle 1 is in one fraction, triangle 2 is in the second fraction. My right sides, right, corresponding sides, they're both on the right, are in the numerator, and my bottom sides, corresponding in the same place at the bottom of our triangle, are in the denominators. That's the setup. I know that sounds confusing. Once you actually get to the work, it'll make a lot more sense, hopefully. Now we just got to cross multiply. Have you guys learned how to cross multiply before? Yeah, right? Okay. So we're going to cross. I'm going to circle up my diagonal terms here. and I'm going to multiply each side together. So I've got 7 times x on one side. That gives me 7x, obviously. There's nothing we can do with that. And then I've got 6 times 14 on the other side. Anyone know what 6 times 14 leaves me with?
84.
84. Great job. What can I do now to solve for x? Divide both sides by 7. Couldn't have said it better myself. What are we left with? 12. X equals 12. So my missing side up here, side length EF, is equal to 12. And this makes sense. Take a look. The bottom of my small triangle was 7. It turned into a 14. How do we get from 7 to 14? Times 2, right? My base got twice as large. So proportionally, my right side should also get twice as large. 6 times 2 leaves me with 12, right? So logically speaking, that's how we can check our work to see if we did it right. 7 times 2 gives me 14. So 6 times 2 should give me that 12. Mathematically, though, this is what we want to do. We set up a proportion. One triangle is one fraction. The second triangle is another fraction. Cross multiply and divide. Just like that. Now, some of you may be more comfortable using a calculator for this, which is fine. But some of these questions, we're going to get pretty large numbers. And it might be easier for us to simplify our fraction before we cross multiply. Let me show you what I mean here. This is the worksheet we're going to get. If I'm looking at number 1, right? And I want to set up my proportion. I'm going to make the big triangle one fraction. All right? What fraction can I make for my first triangle? 60 over 70. Sure. We'll do 60 over 70. Could you have done 70 over 60? Yeah. As long as our second triangle matches up with our first fraction. So I put the top length over the bottom length, right? 60 over 70, top over bottom. So what do I need to put on top for my smaller triangle's fraction? X. Top side, X, over bottom side, 7. So when we're talking about corresponding sides, that's what we mean. Top over bottom equals top over bottom. I could have done bottom over top, but then I would have had to do bottom over top for my second one. And when we cross multiply, we'd end up with the same thing. So this is what I mean when I say we can simplify our fraction first. Because 70 times x gives me 70x. 60 times 7 gives me, I think, 420. Well, now I have to divide this big number by this other big number. Can I simplify 60 over 70 at all? 60 over 70? 6 times 10 over 7 times 10? Is there anything I can cancel out here? 10. The 10s. So now I've got 6 over 7 equals x over 7. Right? All I did was simplify my larger proportion to get 6 over 7. Now when I cross multiply, I get 7x equals 42. I can easily divide that by 7 to get x equals 6. Now you would have got x equals 6 by dividing 420 by 70. But it's a lot easier if we break that fraction down first. It's not something you always have to do. It's It's not something you have to do at all. Again, if you have a calculator and you'd rather use that, you can. Just a little trick to make your life easier if you want to make your life easier.